Hello students, let us start our session of chapter number 7, Systems of Particles and Rotational Motion. Here in this particular chapter, we are going to study in detail about the rolling motion or the object which is following a rolling path. So here the motion of the body is idealized of a particle. And here we are going to understand about that how body first takes place in a system of particles. So here while we want to define a system of particles, so let us take first particle, let us observe its motion, and then we are going to combine its effect, and which defines a system of particles or analysis of system of particles. So here let us consider a rigid body having perfectly definite and unchanging shape. So the distance between all pairs of particles are not going to be changed. Here, this is from this definition of a rigid body. No real body is truly rigid. Since the real bodies deform under the influence of forces, but in many situations these deformations can be negligible. So here the number of situations or examples we can take as a wheels, steel beams, molecules and planets on other hand, that we ignore it's a wrap or twist out of shape, bend or vibrate, and we are treating them as a rigid. So here in this chapter we consider we are taking a rigid body and we are going to analyze over it. So here let us understand what kind of motion can a rigid body have. Here two types of motions can be there, translational motion and rotational motion. So in translation motion, at any instant of time, all particles of the body have the same velocity, as you can see in the first diagram, in which we are taking a rectangular shape of object and it is given in tapered shape path. So from object A to B, while that object is moving, so all the objects are moving in a same direction with same velocity. So here all the particles cannot be moving with the same velocity at an instant, but their direction is same, and that is not a pure translational motion. So in pure translational motion, at each instant of time, all particles are having the same velocity, and in not in pure translational motion, these particles are not moving with same velocity. Now let us take another object who is taking a rolling motion. So the motion of the rigid body, if it is in rotation, so in that case, line or fixed axis about which the body is rotating, that is axis of rotation. Let us take an example, a ceiling fan, a potter's wheel, a giant wheel or merry-go-round. And this thing can be evaluated as the second diagram is given. The object size, that is a circular, and while it is moving from A to B path, so all objects are not taking a same velocity and not taking a same direction, but they all are moving from a center axis, that is the axis of rotation. So in that rotation of a rigid body about a fixed axis, every particle is taking a circular path which lies in a plane perpendicular to the axis, and it's a center on the axis. Rotational motion of a body about a fixed axis, generally we are taking x-axis for the reference. Now as you can see in the diagram, as z-axis is taken as a reference for the fixed axis, let us take particle P1 as you can see in the diagram. That particle of a rigid body that is arbitrarily chosen at a distance r1 from fixed axis. This particle P1 describes a circle of radius r1 from the center C1. Now this circle lies in a perpendicular direction of the axis. Likewise, let us take another particle P2 which is available at a distance r2 from the fixed axis, and P2 again taking a circular path having a radius r2. So C2 becomes its center on the axis. So this circle lies again in a plane perpendicular to the axis. So here these circles described by P1 and P2 lie on different planes, but both are perpendicular to the fixed axis. So if let us take another particle P3 which is onto the axis, so its radius is 0. This particle remains stationary even though the body is rotating. So this is axis of rotation is fixed. This is how we can define. Let us take some of the example for the same. As you can see in the diagram, a spinning top, an oscillating table fan or a pedestal fan. A motion of a rigid body which is not pivoted or fixed in some way is either pure translation or a combination of translation and rotation. Motion of a body which is a pivoted or fixed is some way is rotation. So the rotation may be about an axis that is fixed just like a ceiling fan, or moving just like oscillating table fan. Here in the diagram we can see the same kind of observation. The first diagram defines a motion of a rigid body in a pure translation in which object is not rotating from its axis. Just the whole object by its condition as it is taking a circular path. As you can see in the diagram B, the object is moving by the combination of translation and rotation. So object itself is rotating around its axis, and as well it takes a circular path by taking its translation motion. So while the object takes a black line path, that is a translation motion, and from its own axis while that object is rotating, that is a rotational motion. Now let us understand another concept, that is a center of mass. If we are taking a system having two particles, these particles are joining with a line on the x-axis. So here the distance of these two particles from the origin, x1, at that distance, as you can see in the diagram, m1 object is there, and from the origin at x2 distance another object is available having a mass m2. So these m1 and m2 are masses of two particles. So center of the system let us take as a C, that is at x distance from the origin. So x would be the equation m1 x1 plus m2 x2 divided by m1 plus m2. And this x, this regarded as a mass weighted mean of x1 and x2. If these two particles have the same mass, that m1 equal to m2 equal to m, then this equation can be defined as mx1 plus mx2 divided by twice m. So that is equal to x1 plus x2 by 2. So here the two particles of equal mass having the center of mass that is exactly available at midway between them. So if we are having a system which is having n particles, so its center can be defined onto the x-axis by the same definition, that m1 x1 plus m2 x2 up to mn xn divided by m1 plus m2 up to mn. That is what the addition of mi xi by the limit 1 to n divided by addition of mi by the limit 0 to n. So that would be addition of mixi divided by addition of mi. Here this x1, x2, xn are the distance of particles from origin, and x defines the measured center. And sum of mi, that is a capital M, that is a total mass of the system. So here, now if we have a 3 particles, they are not lying in a straight line. They are not onto the same axis. So in that case, these particles can be defined by the x and y axis in a plane by having their coordinates x1, y1, x2, y2 and x3, y3. And mass of these particles are m1, m2 and m3. So for that, center of mass of this system can be defined by xy coordinates. So x coordinate of the center, that is m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, and y equal to m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Here, if we are taking mass of all 3 particles are same, which is equated as a m, then our x coordinate center would be x1 plus x2 plus x3 by 3, and y coordinate is y1 plus y2 plus y3 by 3. So here 3 particles of equal mass in which the center of mass coincide with the centroid of the triangle formed by the particles. So here we are having the generalized equation for n number of particles in a system having a coordinate 3 dimension in a space x, y and z. So x equal to summation of mixi divided by capital M, y equal to summation of miyi divided by capital M, and z equal to summation of mizi divided by capital M. These 3 equations combined in one equation using the position vector. So here this position vector, let us take Ri, that position vector of ith particle, and capital R, that is a position vector of center of mass. So Ri equals to xii plus xij plus xiy plus yij plus zik, and R, capital R equal to xi plus yj plus zk. So capital R, the generalized equation we are having, summation of mi ri divided by capital M. So here, if the origin of the frame of reference is chosen to be a center of mass, then capital of mi ri equal to 0 of the system of particles, and the number of particles in such a body is so large that it's impossible to carry out its summation. So the spacing of the particles is very much small, can be treated as a continuous mass distribution, and we divide this body in the small element, that is a delta m1, delta m2, likewise delta mn. So that delta mi is taken to be located in a space having the dimension xi, yi and zi. So for that, center of mass can be x equal to summation of delta mi xi divided by summation of delta mi, y equal to summation of delta mi yi divided by summation of delta mi, and z equal to summation of delta mi zi divided by summation of delta mi. And here, if we take a sum over the integrals by taking its extension tends to 0, then summation of delta mi equal to integration of dm, that is a capital M. Summation of delta mi in xi direction, that is xdm, integration of xdm. Likewise, summation of delta mi yi tends to that integration of ydm, and summation of delta mi zi tends to integration of zdm. So capital M is the total mass of the body, and coordinate of the center of mass can be x equal to 1 upon m integration of x dm, y equal to 1 upon m integration of y dm, and z equal to 1 upon m integration of z dm. So here the vector expression we are having in 3 scalar, that r, capital R equal to 1 upon m integration of r dm, the position vector component. So if we choose the center of mass as origin of our coordinate system, that r equal to 0, then integration of r dm equal to 0. So integration of x dm equal to 0. Likewise integration of y dm 0. Integration of z dm 0. So here, by using that symmetry consideration, we can choose the center of mass of bodies lie at their geometric centers. As we can see in the diagram, let us take a thin rod. Here, it's a center O is defined, it's a geometric center onto the x-axis. So net contribution of every pair of integral, and hence the integration x dm itself is 0. So here this the equation at where the point for which integral component is 0, which is a center of mass. So the center of mass of a homogeneous thin rod coincide with a geometric center that can be understood by the reflection symmetry. So this symmetry same can give argument which apply a homogeneous ring, disc, spheres or thick rods or rectangular cross section. For all such bodies, every particle, every element dm available at x, y, z point, and one can take an element of same mass of the point minus x, minus y and minus z. So the result of the integrals of that equations are 0. Means all the above bodies have the center of mass coincide with the geometric center. Let us take example for the same. Find the center of mass of 3 particles at vertices of an equilateral triangle. The masses of the particles are 100 gram, 150 gram and 200 gram respectively. Each side of the equilateral triangle is 0.5 meter long. So here xy axis chosen, as we can see in the diagram, over which the points O, A and B defines at the point 0, 0, 0.50, 0.25 and 0.25 root 3. So here mass of that point having 100 gram at O origin, 150 gram at A point and 200 gram at point B. So here let us calculate the center of mass x equal to m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Let us take x coordinate of the points and substitute the value of mass of the particles. So resultant x value we are having 5 by 18 meter. Likewise for the y component of the center of mass, substitute the value of y coordinates of the points and mass of the objects. So we will get y equal to 1 upon 3 root 3 meter. So here we can say that center of mass in the figure, this is not the geometric center of the triangle OAB. Likewise, let us take another example. Find the center of mass of a triangular lamina. So here lamina having the triangle LMN, that is divided in narrow strips, as we can see in the diagram, that are in the parallel to the base of MN. So by symmetry strip, its center of mass, it is available at midpoint. if we join this midpoint of all the strips, we are getting LP median. So here the center of mass of the triangle as a whole, that is lying on LP median. So we can say that this center of mass lies on the medium on MQ and NR. It means center of mass lies on the point of concurrence of the median at point G of the triangle. Let us take another example. Find the center of mass of a uniform L-shaped lamina, a thin flat plate with the dimensions as shown in figure, and mass of the lamina is 3 kg. So here let us choose x and y axis as we can see in the diagram, and we have the coordinates of vertices which is available in L-shaped of lamina. This L-shaped of lamina consists of 3 squares, each of having a 1 meter length, and mass of the object, mass of each square, that is a 1 kg. So we can say that lamina is uniform in a structure. Now center of mass C1, C2 and C3 of each square by its geometry, and its coordinates are 1/2, 1/2, 3/2, 1/2, 1/2, 3/2, which denoted a center of each square. So now let us take a mass of each square and concentrated at that point. So center of mass of whole L-shaped XY is the center of mass of these mass points. So that x equal to m1x1 plus m2x2 plus m3x3 divided by m1 plus m2 plus m3. Now we are having mass of each square and having x coordinate of each center. Let us place the values. So x would be 5/6 meter. Likewise for y coordinate of the center of mass, m1y1 plus m2y2 plus m3y3 divided by m1 plus m2 plus m3. We are having mass of each square and y coordinate of its center. Let us substitute in the same and we will get y equal to 5/6 meter. So we can say that center of mass of the L shape lies on the line of OD. Clear? Here we are going to end this session. Hope you understood. Thank you.